Welcome back to Integral Calculus. In this video, I want to talk about the calculus with inverse functions. We've been in recent videos talking about logarithms, and I hinted about the exponential function, which is defined as the inverse of the logarithmic function. With that end goal in mind, I thought now was a good time to review the basic definition of an inverse function, look at how we can use calculus to analyze inverse functions, and then look at how we can use properties of inverse functions to simplify some of the tools of calculus. All right, let me get my head out of the way, and let's start just by looking at the definition. Consider a function f mapping from the real numbers to the real numbers. The inverse of this function is another function. We generally denote with a superscript -1. And the definition is that if you evaluate f of f inverse, you get x. And if you evaluate f inverse of f at some point x, you also get x. And yes, it is possible to have a function that does one and not the other. Generally speaking, that's where we use things like branch cuts. Because if I talk about f of x as x squared, and I'm going to denote it as f star because it's not actually an inverse, but the square root of x. Right. F of f star is equal to x if x is greater than or equal to 0. If x is less than or 0, it's undefined. And f star of f of x is equal to the absolute value of x. So it's kind of sort of mostly x if you take just the positive values of x, but if you don't have that restriction in mind, then you run into some issues. So you have to carefully define and take the branch of the x squared function where x is positive, and then yes, you do have an inverse, but as it's written, you do not. Not all functions have inverses. For some function f, we can say that the inverse function exists if and only if f is a one-to-one function. The simple way of testing for a one-to-one function is the horizontal line test. If you sketch the graph of your function, it should be impossible to draw a horizontal line that passes through the curve more than once. Going back to my squaring example, that's exactly where the problem was, right? If we draw a horizontal line, it goes through the function twice. The squaring function does not have an inverse. One of the issues with the horizontal line test is, well, what if your graph just isn't big enough? Right? What if you are looking at a curve that looks like that? But then you zoom out and you realize it does this, way off of the cut of the screen. All right, so the graphical tests I always explain in the introductory college algebra level courses, pre-calculus level courses. The horizontal line test and the vertical test like it are ways of finding when things don't happen. They have no guarantee that something does happen. So the horizontal line test will never tell you that a function is one-to-one and has an inverse, but it can be used very effectively to say the function is not one-to-one and does not have an inverse. In order to get there, we have to be a little bit more precise. And while we're not going to be able to get a perfect tool, we are going to be able to get at least something. So my theorem here says that if a function is monotone increasing or monotone decreasing, then it is one-to-one. I'm not going to formally write out a proof, but I do want you to think about what that means graphically. Right? If a function is monotone increasing, that means that it can never flatten out. That means it can never double back and go down. It has to always be going upward. It can be going upward very slowly, but always going upward. It can be going upward very quickly, but always going upward. Regardless, it is never going to hit a point where it doubles back on itself. And even if you zoom out, it will still never double back on itself. So that is a nice way of testing whether a function is one-to-one. So for example, let's take a look at the function f of x equals x cubed plus x minus 1. Well, if I jump over to Desmos, the graph certainly looks like it's one-to-one. Why am I showing up right above it? I'm supposed to be showing up way over here. Anyway, if I jump over to Desmos, the graph certainly looks like a one-to-one function. But again, I can't prove that if you continue upward indefinitely, it will never turn around. I need to do that algebraically. I need to do that analytically. And the tool that I have, the only tool that I have, is a special case. Right? Every monotone function is one-to-one. Not every one-to-one function is monotone. But I can check to see if the function is monotone by taking its derivative. The derivative here is going to be 3x squared plus 1. And if I graph 3x squared plus 1, I don't need the details here, but right, it's going to be a parabola. And the important thing is it's always going to be positive. If the derivative is always positive, then the function is always increasing. And if the function is monotone increasing, it's one-to-one, and if it's one-to-one, then its inverse exists. Well, we still have a problem here, though. The inverse exists. How do we find it? Well, for that, we can use a couple of other tools of calculus. All right, so going off to the side a bit, we will revisit that function a little bit later. But in general, remember that an inverse function is always set up so that if y is equal to f of x, then x is equal to f inverse of y. And so, if I have a function that has an inverse, and I look at the line where y is equal to x, the inverse function is always going to be the mirror image on that line. Right? So flip the graph over across that line, and you get the inverse function. I did this out of order, so I have to redraw a lot of this, but that's okay. Specifically, I want to look at a relatively simple case. Specifically, I want to look at a relatively simple case. Let's consider this graph. It is a straight line. In general, the equation of a straight line says y equals mx plus b. As lines go, this one's actually not doing all that much, but if I mirror it across that line y equals x, then I get this line, which is x equals my plus b, right? Just swapping x and y. And I can rearrange that to get that y is 1 over m times x minus b over m. All right, that last part's not important. The important part here is that I took the reciprocal of the slope. Inverse functions have reciprocal slope. I can use that to my advantage here, because the slope of a curve is its derivative. So the derivative of the inverse function is going to be 1 over the original function evaluated at, well, whatever point the inverse function spits out. All right, so again, remember, if you have an ordered pair, the x-coordinate, f of a equals b, and the y-coordinate, f inverse of b, is equal to a. So, because we are taking the original function's derivative, f prime of x, well, we don't want to just evaluate at x. We need to evaluate at the point where it came from. So we evaluate the inverse function first. It looks really ugly. In practice, it's fairly straightforward. So let's go back to that function we were talking about a few minutes ago. F of x is x cubed plus x minus 1. Well, let's just pick a point at random. If I evaluate f of 2, that's going to give me, well, 8 plus 2 minus 1. All told, that's 9. And I've written down the derivative here earlier, 3x squared plus 1. If I evaluate that at 2, it's going to give me 3 times 4 plus 1, which is 13. With just that information, well, just flipping it around, f inverse of 9 is 2. That's the definition of f of 2 equals 9. And then f inverse prime at 9 is going to be 1 over f prime of f inverse of 9. F inverse of 9 is 2. And 1 over f prime of 2 is 1 over 13. Okay, yay, I guess. We're able to take the derivative of a function we don't know because we know things about its inverse. But once we're able to take the derivative, we're able to do other things, like a tangent line approximation. So, near x equals 9, f inverse of x is equal to the slope, the derivative, 1 over 13, times x minus the point in question, 9, plus the value at that point, 2. This is not the inverse function. This is an approximation of the inverse function. But if we want to be evaluating the inverse function near that point, then we have something to work with. This is a great way to go from an approximation in a graph to something a little bit more analytic. Right? If you are able to graph the original function, you might be able to find a nice integer that's kind of near where you're trying to evaluate. You plug that integer in, you see what happens, and then you go from there. You can use that to find the derivative. You can use the derivative to write the equation of the tangent line. You can use the tangent line to approximate the value of the inverse function a little bit closer. And if you really have to get high precision, you can repeat this process. If you're lazy and you really want this to work out, you can design a computer program to repeat this process for you. And you can get a pretty exact value of an inverse function even if you can't write it out. Right? It's not what we call an exact value in mathematics, but for engineering, physics, chemistry, computer science, well, exact values are completely useless in most cases anyway. All right. So that's what I want you to play around with here for a problem for you to try. You know that f of x is 1 to 1. You know that f of 1 is 3. And you know that f prime of 1 is 2/3. I claim that that's enough information for you to write a linear approximation for f inverse near x equals 3. I'd like you to take a couple of minutes, see what you can do with that one, and I'll see you in the next video.